Okay, welcome back for the third time. Sorry about the confusion this morning. It's well after 11:30, so we'll go ahead and get started. Apparently, you've seen me use my calculator that's in my computer before, but apparently there's a problem between it and Zoom, and when it's on the screen, I can't open up other share functions. Okay, today, as you can see, we're going to be doing section 4.2 on exponential graphs and applications. Okay, we'll go to the slideshow. And now we're ready to go. Okay, in this section, again, we're going to be dealing with exponential functions. What's going on here? Well, I guess we won't use the PowerPoint in slideshow mode. Okay, previously we've had equations like this: y equal x squared, y equal x cubed minus 1. Now we're going to be dealing with equations like y equals 2 to the x, y equals 3 to the x minus 1. In other words, now the variable is the exponent. This is just the definition of an exponential exponent. It's simply saying that the x is the exponent and the number is the base. Here's our first example. Now, when we had the equation y equals x cubed, here would be the graph of it in green. Still not going to do it. Okay, with this graph in green, you can see how it goes both the positive and the negative values. Now, let's look at 3 to the x power. If x is 0, okay, then y is going to be 1. By the way, this graph goes up by 2's. Okay, if x is 1, then y is 3, right here. And if x is 2, over here. Now this one, the horizontal line goes standard. So if x is 2, then y is up to 9, or 3 to the second. And if x is 3, we're way up here to 27. So you can see the graphs of those of exponential and just powered graphs are very different. Okay, in this case, we're doing a transformation on these. If you remember earlier, okay, wow, my computer's really acting goofy right now. If we changed x to negative x, we would flip it across the y-axis. Well, that happens with this as well, okay? It happens the same way because the graph of 2 to the x would go this way. So 2 to the negative x flips across the x-axis and is decreasing. This ties in with the idea on lines. If you have a negative x, the line goes downwards. Well, this is decreasing. If you had a positive x, the line goes upwards. So that's still consistent. Okay, here are two functions to graph. 5 to the x and x to the 1/5. Now this is something different. Well, first of all, 5 to the x. You start here, you go through the point 0, 1, then you go up through the point 1, 5. Okay, and you can see what the XY table would look like for this. And if you have -1, then you have 1/5. And -2, you would have 1/25, and so on. Now, let's talk about these two. These two, if you notice, this and that are the same, because if we take x to the -5, that means we have 1/5 to the x. Okay, because that negative exponent, if you remember, flips the base value upside down. Well, no matter which one of these you use, and this one's the easier one, here would be your set of values that you would get. Okay, now both of them go through the point 0, 1 right here. But in this one, if x is 1, this is 5. Here, if x is 1, it's 1/5. If x is 2, okay, if x is 2, then it's 1/25, just like it's 1/25 over here for -2. And if x is -1 in the black graph, then we go up to 5. So you see these two, this one, 5 to the x, and x to the 5 to the -x, are reflections across the y-axis. Okay, here's another equation. Now, if we just start with the basic equation 2 to the x, this is the graph of it in red. Now, what is all this stuff going to do to it? Well, that +1 is going to move the thing one place to the left. This negative right here in front of the 2 is going to flip it upside down, and then the 1 is going to raise it up 1. So those are the different functions. The transformations work on these just like they did the other things. Okay, here's another one. Again, here's the parent graph. Y equals 2x. And the graph of it over here in red. Now, we want to find just, this is actually an analyzation of the same one we just finished. This is just an expansion of what I said. First thing you do is you start with that x minus h up at the top, or in the case of this exact problem, x plus 1. And you see if x is a positive number, if x is greater than that, you shift to the right. If it's negative, you shift to the left. And actually, those are wrong. Okay. What that's meaning, though, the reason this is a little confusing, perhaps, because if h is greater than 0, then you would use x minus 1, because it's always opposite of sign, the direction you shift. If x is a negative number, then you would end up with x plus the number and shift to the right. In this case, we have it shifted to the right, or excuse me, to the left, because this is positive, an opposite of sign there. Okay, This number in front of the base, in this case, is -1. So that's going to flip it across the x-axis. And then the k value, which in this case they had up in front, is going to move the whole graph up 1. Now, you will have test questions where I'll give you something like this problem, and you have to tell me what transformations will happen. So you would say 1 to the left for this, then 1 up for that, and flip across the x-axis, except actually those two should be reversed because you should work from the inside out. Okay, here's another one. 2 to the x, the graph in blue. Okay, this one, which is the same thing as 2 to the -x, because in this case, if you've got 1, then 2 to the -x would be 1/2, and so on. So anyway, it goes in this manner, just reflected across the x-axis. Another example, this time with 3 to the x, okay, and 1/3 to the x. Well, 1/3 to the x, again, is the same thing as 3 to the -x. So what we can do then is, in this case, it's going to be a reflection of this one. And we can just plot points opposite lengths across the y-axis. Here's the XY table if you want to do it that way. Still not going to do it. Okay, on the next example, once again, I have 1/3 to the x power. That's the same thing as 3 to the -x power. Okay, if here is 3 to the x, then here is 3 to the -x. A generic one, anything to the x is going to generally go up in that shape. Anything to the -x is generally going to go in that shape. Okay, both a number to a power and a number to a negative power are called an exponential growth function. In other words, if this is positive, then you're going to grow increasingly or upwards. If that's negative, then left to right, you will go downwards, and they call it a decay function. What about the domains? Well, the domain of both of these is infinity to infinity because these keep going outwards as well as upwards. Now, here's one we're going to do the transformations on. First, we're going to shift it 2 places to the left. So I take this red graph and I shift it 2 places to the left. That's this blue line right here. Then I'm going to take it down 1. So I take all of these points in this one and I shift them down 1. Okay, this one and this one. And I haven't drawn it perfectly. But basically, the x plus 2 is going to take you left 2 places. The -1 is going to take you down 1 place. Now, base E. This is how they came up with the value of E. E is a number kind of like pi. It just keeps on going forever. It never stops. Just keeps on going. And with it, you just, they got it by using the compounding interest formula, basically. Now, it works out to be 2.718. You need to memorize that 2.718, okay? Because you will have to substitute it into some problems. Either that or use your calculator. Now, what you'll want to do then, if you notice this is almost 3, so the graph of e to the x is going to be real close to the graph of 3 to the x. Now, let's see how you would find some values of e. In this case, I'm going to use as my example e to the second. In your calculator, you would first punch the alpha key, and then down here, there's a little e up in the corner of that key, and you punch it. That would bring up your letter E. Then you put the variable power. Now, if you just wanted x squared, you could use the x squared key, but we may want to change to a different power from time to time. So in this case, we're just going to use this. We're going to use this x to the whatever key, which puts the place for the power. Now, if we're wanting x squared, then the next thing we do is push the 2, which gives us e to the second. And then finally, we hit the equal sign to get our answer of 7.398 or 389 and so on, which we would typically round off to 4 significant digits. Okay, looking at these. If you've got your calculator, try these. Okay, here's e to the second. Same thing we got a moment ago. Now, backing up here. If you go with the back key, these 4 right here, you can back up to behind this 2 so that you've got this. Then hit the delete key, it'll erase the 2, and you can put in a 3 or a 5 or whatever new number you want to, instead of starting all over from scratch every time. So in this case, e to the -3 is that value. E to the square root of 7, if you would ever have a reason for that, is this. And e to the pi value would be this. We're going to graph e to the x plus 1. In other words, we're going to move the e to the x graph one place to the left. In red, we have the e to the x graph. It's very close to the e to the 3 graph. Okay? Goes up here through, and each one of these blocks is 2 vertically and 1 horizontally. So it goes up to the point 0, 1, then 1, 0, or 1, 2. Now the graph of 3 would be up here. The graph of 3 to the x is just a little bit steeper than the graph of 2 to the x. Anyway, here are the values you can get with your calculator and graph them. You will need your calculator for test 4, which will be in person again. Now, this is another problem where you're asking for transformations. They're wanting to know what effect that -1 there has and what effect this -1 here has. Well, first, the x minus 1 shifts the graph one place to the right. Okay, so if here's e to the x in red, the x minus 1 would shift this graph one space. You can see here, you can see here. one space over to the right. Now, the negative in front then would take this graph and flip it upside down across the x-axis. Okay, now we're going to use exponential equations to compute compound interest. There are three equations here, and you need to memorize all three of these. You'll be expected to know all three of them for the final as well as my test. This is what they call simple interest. Okay, this one right here. I equal PRT. Interest equals principal times rate times time. This second one is the ending amount equals how much you started with times 1 times your interest rate over how many times you're compounding it per year, and then to the power of how many times you're compounding it times how many years. This one is what they call continuous compounding. Okay? Now, the amount you end up with is the amount you start with times e to the interest rate times the number of years. That one's actually very simple to use, much easier than this compounding version. So let's look at this example. 15,000, that's your P value, your principal, the amount you borrowed or the amount you invested. The interest rate you have to change to a decimal. Now, here are the compounding options. Okay, if we use once a year compounding for 7 years is what this is saying. Okay, the principal 1,500 times 1 plus this over once a year times once a year times 7 for the power, and you basically put all that into a calculator. You'd hit 15,000 parentheses 1 plus 0.025 parentheses x to the power key 7 equals, and it would give you that value. Okay, for compounded quarterly, that means we're going to compound it 4 times a year. So the 15,000, the 1 plus 0.025 over 4, and 4 times 7 is 28. Okay. Now, you can actually use the fraction key and put this in this way, the way it looks, if you want to on those calculators. Notice the difference in earnings by compounding 4 times a year compared to 1 time a year. 17,858 plus 17,830. So in other words, it got you an extra $28.96 by compounding quarterly. Now, continuously, that means that we're going to do it continuously, infinitely many times. The amount 15,000 times E, okay, and you would put in 15,000, you would hit that alpha E, X power sign, enter this just like it looks, equals. Continuously, you picked up another $10. So the more times that you compound, the more money you will earn. If you borrow 12,000 at 5% for 6 years, how much are you owed if you are charged? Simple as quarterly, daily. Daily is almost going to be the same as continuous, but it'll be slightly less, maybe a matter of pennies. And then infinitely. Okay. Here are your formulas. We've talked about them before. Now, here's an example. Suppose 8,000 invested pays 4.5% per year. Determine after 5 years. Well, what we would have then is we would have for compounded annually, the principal would be 8,000, 0.045, one time a year, 5 years. So we would have 8,000 times 1 plus 0.045 over 1 to the 1 times 5 or 5/5 power. Okay, what if we compute it quarterly? That means 4 times a year. Well, we've still got the same principal. We've still got the same interest rate. Now we're going to have a 4 here, and we're going to have 4 times 5 or 20 for the power. In the case of monthly, that means we're going to do it 12 times a year. So the interest 8,000, the rate 0.045. Now we're going to have in here 12 for monthly, and 12 times 5 is 60 for the power. And daily, we're going to have 365 here for N and up here. So that one's going to get pretty big, but that one in example D is only going to be pennies more than pennies less, excuse me, than if we do it continuously using this formula. Now we're going to do some applications. Okay. Estimate of the population of Mexico in 2010 was 111 million people. By record keeping, they say that the population grows about 0.994% or 0.00994 every year. At this rate, what will their population be in whatever many years it is from then? We're only going to calculate once a year. So in this case, N's going to be 1. So all of this information is fixed with the exception of the amount of time. All right, so let's continue this. What if you wanted to know in 2014, 4 years later, what's their population going to be? Well, you take the 111, the 1 plus 0.00994 over 1 gives you this, and 4 years, since N is 1. That means it'll be approximately 115 million in 2014, or it would have grown 4 million. Or, yeah. Okay, what about 75 years? What do they expect the population to be? Well, everything's the same except the number of years, and they figure 233 million, or more than double. There's one more topic we need to cover today, and that's solving exponential equations. Equations with variables in the exponents, like these, Okay. 3 to the x equals 40. Now, or 5 to the 3x equals 25. The point is that we have a variable in the power. Okay, those are called exponential equations. Now, for this, we've got this power, this property that says a to the x equals a to the y. And if that's true, since you've got the same base, then x and y have to be the same. Now, here's an example of an actual problem on this. This one has a fairly easy solution. Not all of them have this easy of a solution. Okay. Well, here we go. 5 to the 2x minus 3 power equals 125. Well, I don't have the same base on both sides right now. But you know what? 5 is one of the powers of 125. 125 is 5 to the third. So we can rewrite this 125 as 5 to the third. Now we have the same base. That gives us then the equation 2x minus 3 equals 3. Take the 3 on the other side, divide both sides by 2, and we get x equals 3. Let's check that. 5 to the 2 times x minus 3 equals 125. 5 to the 2 times 3 minus 3 power. 2 times 3 is 6. 6 minus 3 is 3. So 5 to the third equals 125. And 5, 25, 125, 5 to the third indeed is 125. So it's true, and the solution is 3. Now, we've got that rule, and we'll expand on it a little bit more. At that point, we're going to have to get problems that don't break down like this one. Let me get my mouse back. To get problems where it doesn't break down to the same base, we're going to have to use some other skills that we're going to start on Monday. Now, this is where we're going to stop for today. And hopefully my computer will be working better tomorrow. So we'll see I suspect I'm going to have to restart the computer to get it to working back like it ought to. So at any rate, you get out a little early today. You can get started on this material in Alex if you wish, and have a good Monday. We'll take up logarithms tomorrow. Let me get out of this. Any questions at this point? Well, if not, we'll see you tomorrow.